Let's practice some more integrals by simplifying them using trigonometric identities. In the last video, we looked mainly at powers of sine and cosine where there was an odd power. We saw a strategy for how to handle this type of integral. The strategy is written right here if you care to read in detail, but I think learning by the examples is the best way to understand how that principle worked. We looked for an odd power on one of the trig functions, we peeled off the odd power, and we used a Pythagorean identity, then did a u substitution and found the answer. Let's look at examples 5 and 6. Notice the difference. We have powers of trig functions, but notice that we only have even powers, cosine squared and cosine to the fourth. If we have only even powers for sine and cosine, we are not going to use this same strategy. Instead, we will use something called the half angle identities. We will use these identities. Sine squared equals this, cosine squared equals this. Let's see how to apply these identities for examples 5 and 6. So for example 5, we have the integral of cosine squared of x. Now we might be tempted to rewrite cosine squared as 1 minus sine squared. We've used this identity before, and it seems reasonable. We could do that, but if we do, we're only rewriting the problem in terms of sine squared, which is still a trig function to an even power, and it doesn't actually help us that much. So rather than using the Pythagorean identity, we will use what's called the half angle identity. From the front of the handout, this is the half angle identity for cosine squared. It is 1/2 times 1 plus cosine of 2x. So we make that substitution into the integral. Cosine squared is 1/2 times 1 plus cosine of 2x. 1/2 is a constant, so we take it out front. And then we have the integral of 1 plus cosine of 2x dx. The antiderivative of 1 is x, and technically we would use a u substitution to solve the antiderivative of cosine of 2x. We'll skip the steps here. This is one of those substitution problems that we want to be able to solve without having to write all of the steps of u substitution. If you want to write them all out just to double check, I encourage you to do so. But we really should be able to identify u substitution here without writing all the steps. If we were to work through it, u we would choose as 2x, and we'd proceed from there. But let's write it without working through all the steps. So we integrate 1. The antiderivative of 1 is x. The antiderivative of cosine is sine of 2x. And to compensate from the chain rule, we divide by 2. We add plus c, and we have the final answer. Now let's just really quick double check to make sure that our derivative of sine of 2x over 2 equals cosine of 2x. So the dividing by 2, that just means we multiply the entire expression by 1/2. The derivative of sine is cosine of 2x. And according to chain rule, we'd multiply by the derivative of 2x, which is 2. That would cancel with our x in the denominator. The 2 in the denominator, and we would have cosine of 2x. This is the correct antiderivative. Let's take a look at example 6. We have the integral of cosine to the fourth. Once again, there are no odd powers, so we have to use the half angle identities. I'm going to rewrite this as cosine squared, and now use the half angle identity for cosine squared. Just as we had in the previous problem, cosine squared can be written as 1/2 times 1 plus cosine of 2x. This is all in the parentheses where we're squaring. So I need to square this entire expression. All right. I'm going to start by squaring the 1/2. 1/2 squared is 1/4. That's a multiple, and I'll just take that multiple out in front of the integral. So the 1/2 squared becomes 1/4. I'll remove that to the outside, and I'll just write an intermediate step here. I still have 1 plus cosine of 2x, quantity squared dx. Now I need to FOIL this quantity here, and I'm going to skip through the intermediate steps. If you feel a little bit rusty on foiling, then you probably want to pause the video, make sure that you can FOIL out this binomial, and if you do, you will get this expression. 1 times itself is 1. We have cosine of 2x plus cosine of 2x, so 2 cosine of 2x, plus cosine 2x times itself, cosine squared of 2x. Now, we can integrate cosine of 2x. That's a substitution. Notice that we have another power of cosine, cosine squared of 2x. How do we deal with this? We will use the half-angle identity again. Let's write down that half-angle identity. And I'm going to write it in terms of y instead of x, just because we already have a 2x here, and we can get a little bit confused with how that works. So I'll write the half-angle identity as cosine squared of y equals 1/2 1 plus cosine of 2y. All right, this tells me when I rewrite cosine squared using this identity, I have to multiply the input by 2. So I'm going to multiply 2x by 2. I'll have cosine of 4x. So I apply the half-angle identity once more. I'll just copy down this 1 plus 2 cosine of 2x. Now I apply the half-angle identity. 1/2 times 1 plus cosine of 2 times 2x. I double the input. So this becomes cosine of 4x dx. Now notice, we have trig functions, but they're all raised to the first power, and we can solve them using a simple substitution. So let's finish this problem. I still have the integral of 1 plus 2 cosine of 2x. I'll distribute the 1/2 into both of these terms. So I have 1/2 plus 1/2 cosine of 4x dx. One more step to simplify, then we'll take antiderivatives. I have a 1 plus 1/2, that's 3/2 or 1.5. I'll just write it as 3/2, plus 2 cosine of 2x, plus 1/2 cosine of 4x. We could work through all the steps of u substitution to solve these two integrals using u substitution, but they're the simple type that we want to be able to write down without having to proceed through all the steps. So now we can write the answer. 1/4 times the quantity, 3/2 x. The antiderivative of cosine of 2x is sine of 2x divided by 2. So I have 2 times sine 2x divided by 2. The antiderivative of cosine of 4x is sine of 4x divided by 4. 1/2 times sine of 4x divided by 4, add a plus c, and there is our answer. We could double check if we took the derivative. The derivative of this rather long expression is cosine to the 4th of x. Let's take a look at problem 7. Problem 7 looks different from the rest. The difference is we do not have powers of sine and cosine. Instead, we have multiples of x inside the parentheses. So we will not use the Pythagorean identities or the half-angle identities. We will use these product identities that are written here on the front page of the handout. All right, how do we apply these trig identities? Well, let's copy down problem number 7. We have the integral of cosine of 5x times sine of 3x. I have a cosine function times a sine function. So I'm going to look at the identities for this. If I have cosine times sine, I will use this particular identity. I'll go ahead and copy that down. Our product identity for sine times cosine, we have sine of A times cosine of B. We can write this as 1/2 times sine of A minus B plus sine of A plus B. All right, the order is actually reversed here in the integral, we have cosine times sine. So I'm going to rewrite the order. I can just interchange the order since I'm multiplying. So sine of 3x times cosine of 5x. And now it's in the form that I can apply the identity. A is this 3x, and b is 5x. So using the identity, I have 1/2 times the quantity sine of a minus b, that's 3x minus 5x, plus the sine of a plus b, 3x plus 5x. There's the product identity applied to the integrand. Now we'll simplify in the parentheses here, and let's take the 1/2, move it out front, and take antiderivatives. 1/2 times the integral 3x minus 5x is a negative 2x, so I have sine of negative 2x plus sine of 8x dx. Both of these trig expressions are U substitution problems, but once again, these are the simpler sort where we want to write down the answer without having to go through all the steps of substitution. We'll write the answer, we'll double check, and then we'll be done with the problem. The antiderivative of sine is negative cosine of negative 2x, and to compensate from chain rule for the negative 2, I divide this by negative 2. For the second function, the antiderivative of sine is negative cosine of 8x, and again I divide by 8 to compensate for chain rule. Add a plus c, this is the answer. Let's just double check going from this to sine of 8x by taking a derivative. If I take the derivative of negative cosine, I have positive sine, and I would have sine of 8x from chain rule multiplied by 8. The 8's would cancel, and I have positive sine of 8x. So here is our solution. When we do not have powers of cosine and powers of sine, when we have instead multiples on the inside, we will use these product identities. Finally, let's take a look at example 8. The integral of tangent to the 7 times secant. This one's different because instead of sines and cosines, we have tangents and secants. We can adopt a similar strategy that we used for powers of sines and cosines to solve powers of tangent and secant. One little fact that we want to remember before we start is that the derivative of secant is secant of x times tangent of x. This is from Calculus 1. We will use this concept as we work through the problem. All right, so I'm going to peel off a power of tangent. I have tangent to the 6 times tangent times secant. Now notice, tangent times secant is the derivative of secant of x. All right, that will be important when we get to the substitution step. Now we have a Pythagorean identity that relates tangent squared and secant squared. The identity is 1 plus tangent squared of x equals secant squared of x. I can solve this for tangent. Tangent squared equals secant squared minus 1. So I'm going to take this original integral and rewrite tangent to the 6 as tangent squared cubed times tangent of x secant of x dx. Now, we rewrite tangent squared as secant squared minus 1 quantity cubed times tangent x times secant of x. Now we will use U substitution. We choose U to be secant of x. The derivative of secant is secant x times tangent x. So dx is du divided by secant tangent. And now we can make the substitution. We have the integral of secant squared, which is now u squared, minus 1, the whole thing cubed, times tangent of x times secant of x du divided by secant of x tangent of x. These all cancel, and we're left with the integral of u squared minus 1 quantity cubed du. At this point, we have just a polynomial in terms of u. To finish the problem, we would have to expand out this binomial raised to the third power. We'd have to FOIL it out. That would be rather tedious algebra. So for this particular problem, the value is to see how to use identities for tangent and secant in order to express the integral in terms of a simpler function. We could finish the problem by expanding out, taking antiderivatives. If you have the time to do so, I encourage you to try it, but we'll leave this one right here.